So let's do some examples here. Coming back to this idea of charcoal, I've got a 31.5 gram brick of charcoal. It's burned in an atmosphere of 102 grams of oxygen. We want to know how much carbon dioxide is going to be made. So to do this, we need our balanced chemical equation. And we need our amounts of each one of these. So we're going to need a little bit more space than what I have here. So I'm actually going to switch over to the whiteboard. And if you didn't copy everything down, that's okay. We're gonna recreate it on the whiteboard here. So we have carbon plus oxygen making carbon dioxide. We've got 31.5 grams of carbon reacting with 102 grams of oxygen. And the question is, how much carbon dioxide are we going to make? Now, to answer this, we're going to follow the exact same procedure that we did in the cheeseburger example. We're going to take our 31.5 grams of carbon and we're going to convert it into carbon dioxide. And we're going to do the same thing with our 102 grams of oxygen by taking it and converting it to carbon dioxide also. Now, it's important that in these calculations that we are doing, that we end at the exact same place. So it's not just good enough that we end up at carbon dioxide. We have to have the same unit for carbon dioxide as well. So since we're ultimately going to go to grams anyway, we're going to make both of these into grams of carbon dioxide. If I didn't do this, if I turned this into grams of carbon dioxide, but this to moles of carbon dioxide, I wouldn't be comparing the same thing, and I'd end up in the wrong place. Similarly, if I went and turned this into grams of oxygen and compared it to the grams of carbon dioxide created by the oxygen, that wouldn't be the same thing either. Grams of oxygen and grams of carbon dioxide are not the same thing. I wouldn't be able to make the same kinds of comparisons. So ultimately, what I have to do is that direct comparison between the two. So let's start with our grams of carbon. And we know that our first step, if we follow our mole map, is going to be to convert those grams of carbon into moles of carbon. The ratio we get from our periodic table, 1 mole of carbon is 12.01. Grams of carbon. My grams of carbon cancel. My second step is to turn the moles of carbon into carbon dioxide. I get that from the balanced chemical equation. Luckily, my balanced chemical equation shows that everything is 1 to 1 to 1. So 1 mole of carbon is equal to 1 mole of carbon dioxide. My moles of carbon cancel. My last step is to turn the moles of carbon dioxide into grams. So I need moles of carbon dioxide in the denominator, grams of carbon dioxide in the numerator, 1 mole of carbon dioxide. Molar mass of carbon is 12.01 plus 16 times 2 for 44.01. And so if I do out the calculations here, I get 31.5 multiplied by 44.01 divided by 12.01 to 3 significant figures. I get 115 grams of carbon dioxide. Now, if this was the only piece of information I was given, if I did not have this last piece right there, then I would be done. I would say, okay, the yield here is 115 grams. But since I don't know that, since I have that other piece of information right here, but since I have this, I got to do the next step. I got to compare it to how much I'd have gotten from the oxygen. And so I have 102 grams of oxygen, and I'm going to need to convert that. So grams of oxygen in the denominator, moles of oxygen in the numerator. 1 mole of oxygen, 2 times 16 is 32. So my grams of oxygen cancel. I now need to take my moles of oxygen and turn it into moles of carbon dioxide. And so one of the wonderful things about the limiting reactant problem is that a number of the things that we do end up being somewhat redundant. So my mole-to-mole ratio, obviously the dioxide is going to be the same. In this case, the oxygen's the same as well. And then the last step, where I convert the moles of carbon dioxide into grams of carbon dioxide, well, what do you know? That's the same as well. And so 102 times 44.01 divided by 32 will give me 140 grams of carbon dioxide. And so what can we say about this? Well, we can say that this is our theoretical yield. 115 grams of carbon dioxide is our theoretical yield. Carbon is the limiting reactant. Oxygen is in excess. (115 grams of carbon dioxide is the theoretical yield. So we can say all of these things based off of these calculations. Now, the only other thing that we could possibly say is if we wanted to know How much excess reactant is left over? Well, there's a number of different ways to approach this problem. You can take it a number of different directions. One way is you start with the limiting reactant, 31.5 grams of carbon. You convert it to the excess reactant, the oxygen, and you just subtract that amount from the excess that you started with. So let's say I do this calculation. It tells me that I would have used 80 grams of oxygen, and so I subtract 102 minus 80, and I get 22 grams of oxygen left over. The other method is I take my two yields, I subtract them from each other, and then whatever that difference is, that's the excess yield. And I just convert that back to excess reactant. In my mind, that's actually easier to do. Either way works. You'll get the same answer, or at least roughly the same answer. But this one kind of takes advantage of a lot of the work that you already did. So just as a illustration, I'm going to show you this this second method. So we start 140 grams of CO2 minus 115 grams of CO2 would give me 25 grams of CO2. And so it's this 25 grams of CO2 that I'm ultimately going to be working with. And what I'm going to do is I'm going to go back from CO2 to grams of oxygen. So luckily, all of the legwork has been done for us already in this conversion. Basically, I'm just going to take this conversion and flip it around, reverse it. So 44.01 grams of CO2 in 1 mole of CO2. One mole of CO2 is equal to 1 mole of O2. And then finally, 1 mole of O2 is equal to 32.00 grams of O2. And if I do this calculation, 25 times 32 divided by 44.01 to two significant figures would give me 18 grams of O2 left over. Now, like I said, you could have run this back and done it the opposite way. 31.5 grams of carbon, and if we had done it that way, let's just take this out here. (31.5 grams of carbon, and then following the map here along, 12.01 grams of carbon in 1 mole of carbon, 1 mole of carbon in 1 mole of oxygen, 1 mole of oxygen in 32 grams of oxygen. If you had done that calculation, 31.5 times 32 divided by 12.01 would give you 83.9 grams of oxygen used, 102 grams of oxygen minus 83.9 grams of oxygen used would give you 18 grams of oxygen left over. So you could have done it either way. Like I said, both processes involve a stoichiometry and a subtraction. It's just a matter of which order you do them and what you start with. Idea is the same either way. Any questions about this particular example or about the side street we just went down with regards to excess reactants?
No.
All right, then let's get back. And I'm going to let you do one now. So we've got acetylene. Acetylene is used by welders in torches to make welds at temperatures up to 3,500 degrees Celsius. If 52 grams of acetylene and 188 grams of oxygen combine, according to this unbalanced reaction, which is the limiting reactant? How much carbon dioxide do we get? Now, just to get the ball rolling a little bit here, let's go ahead and balance this together and make sure that we're on the right page. And so we've got the thing balanced now. Just a little trick that can help to balance that quickly. When we have combustion reactions like this, a real key to knowing whether or not you're going to need to double it or not comes in what you do with the hydrogens. If to balance out the hydrogens, you end up with an odd number in that spot, you know that you're going to have an odd number of oxygens on this side, which means you're going to have to double everything so that you can get it to even up here at the end. So that's how I knew to start with a 2 here as opposed to just a 1, because with 2 hydrogens here and 2 hydrogens here, that meant that I was going to have an odd number of oxygens. At any rate, go ahead and try to solve this one on your own, and we'll come back in a few minutes and talk about it. All right, so if you're still working, go ahead and keep going. We'll get kind of the process started, and you can kind of check yourself and your progress. So the thing that we're doing here is, since we're trying to figure out how much carbon dioxide is generated, we should use that as our ending point. So in the end, we are going to figure out the number of grams of carbon dioxide for each one of these. Now, the process to get there, again, relatively similar, but different starting points. So the first thing we need is the molar mass of acetylene. Molar mass of acetylene, 12.01 for the carbon times 2, 1.01 for the hydrogen times 2, 26.04 grams is the molar mass. So 26.04 grams of acetylene in every mole of acetylene. Now we want to use our balanced chemical equation. Two moles of acetylene is equivalent to 4 moles of carbon dioxide. And as we saw before, 1 mole of carbon dioxide weighs 44.01 grams. Now, if you're not sure where we got that, that's been the molar mass we've been using for carbon dioxide in pretty much every other calculation that we've done thus far. And so if I carry all of that through, 52 times 4 times 44.01 divided by 26.04 divided by 2 to 3 significant figures would give us a yield of 176 grams of carbon dioxide. So that's part one. We have no idea whether or not 176 is a high number, a low number, or the right number.
Okay, I got this. I'm sorry to interrupt you. I got the same answer. I'd have already been say something. I had got the same answer, but I did not get it how you got it.
Okay.
So I was trying to see how you went on ahead and wrote yours out before I said something. So I did come up with 176.
Okay.
So what happened was I did the 52.0 C2H2 times 1 mole C2H2 over 5208, but I wasn't for sure if I needed to go ahead and put, I don't know. I know that it's like 4, the carbon is 4, the hydrogen is 4. So I didn't know if it was supposed to be 2 moles per whatever or what, but like I put 1 mole is 5208. And then the second one, I said times 1 mole of CO2 over 1 mole of C2H2.
Okay, so I'll tell you what, you kind of lucked into the right answer. Because basically what you did, for whatever reason, you doubled the molar mass down here and then did not double the mole-to-mole ratio. So you didn't double when you're supposed to here, and you doubled down here when you weren't supposed to. So the mistakes kind of negated each other. And you kind of got lucky.
Because after that, I put times 176.044 grams of CO2 over 1 mole of CO2. And then I did the multiplication and division. So
okay. So I see what you're doing. The problem with what you're doing is the only time we need to apply these numbers in the balanced chemical equation is in this middle step right here. So these numbers, the 2, the 5, the 4, the 2, only get applied in this step right here.
Okay.
Everything else is just a molar mass, 1 mole of the substance for whatever the sum of the masses on the periodic table is. To do what you were doing, you would have needed to, instead of, you said 176 here for carbon dioxide.
Because you needed to find the mole.
You
Yeah.
would have had to put a 4 down here.
I knew that. And that's what I wasn't, because looking at it, when you balance something, I felt like to get the answer, they want like, well, you got 2 of these now. So you need to, I just felt
No,
like, okay, never mind. Okay. Well, I'll just go ahead and treat
this
one.
step and this step require molar masses. Molar masses, by definition, are for 1 mole of the substance.
Yeah. Yeah. So I felt like I was supposed to put 2 over 5208.
No, if you do
Okay.
that, that's fine. But it's an extra step that you don't need to do.
Okay.
You can just do 1 C2H2 and 1 CO2.
Okay.
The numbers that you're talking about come from the balanced chemical equation, and they are only addressed in this step right here.
Okay.
So when we do the mole-to-mole conversion, when we're converting
Yeah.
from one substance to another, that's when we pay attention to the coefficients.
Okay.
That's when we start putting those numbers in. Otherwise, we don't need to even worry about them. That could, the number could be 30 for all we care. We're still
Yeah.
only going to calculate the mass of 1 mole.
Okay.
Okay. So, yeah, you end up coming to the right answer. You just took what I would call the extremely long road to get there.
Okay.
So, watch out for that. Watch out for that when you're addressing these kinds of things. Make sure that when we're doing these kinds of calculations, we don't have to overcomplicate them.
Okay, because you did account for it, because I felt like you need to account for it. So you accounted for it when you put 4 over 2. That's
Yeah,
fine.
this is
'Cause
where
I
you
wanna,
account for it.
okay. Yeah, that's fine. I understand that.
Okay, so based on the acetylene, we expect 176 grams of carbon dioxide. Let's do it out for the oxygen and see if we end up in the right or in the same spot or a different spot, and take it from there. So 32 grams of oxygen in a mole. This time we've got 5 moles of oxygen for every 4 moles of carbon dioxide. And 1 mole of carbon dioxide is still 44.01 grams. So if I do that calculation, 188 times 4 times 44.01 divided by 32 divided by 5 to 3 significant figures again, I end up with 207 grams of carbon dioxide. So again, we choose the lower of the two, 176. That becomes our limiting reactant and our theoretical yield. So limiting reactant is acetylene. Oxygen is in excess. 176 grams of carbon dioxide equals the theoretical yield. Again, as we talked about yesterday, we can use that theoretical yield and compare to, let's say that we did do this reaction in the lab and it generated 159 grams of carbon dioxide. We could compare those two and get a percent yield, get an idea of how efficiently the reaction ran.